Our goal in this video is to develop what's called the Euclidean algorithm, and in particular, it's an algorithm which gives us a method for computing the GCD of any two integers a and b, and also gives us integers u and v that allow us to write the GCD of a and b as a linear combination, or an integer linear combination of a and b. So up until this point, we have some existence theorems about these things, but we don't have anything about how to actually find these quantities. Before we do this, we need to prove two very quick facts. The first fact that we'll prove is that if a, b, and c are integers, and c divides a and c divides b, then c will divide any integer linear combination of a and b. So c will divide anything of the form am plus bn, where m and n are integers. So this is a quick proof. So let's do this. It's also a good exercise to try. So let's begin our proof. I'll say, suppose c divides a and c divides b. So then there exist some integers, let's say j and k, such that a is equal to cj and b is equal to ck. Okay, so let's look at our expression. We could then say that am plus bn can be rewritten as cjm plus ckn, which we can now rewrite as c times jm plus kn. And this immediately gives us that c divides a, so c divides am plus bn. So now we have, hence, c divides am plus bn. Okay, so that's our first very quick proof, and it's one of the facts that we'll need in when we prove that the algorithm we develop actually does what it's supposed to do. So our second claim says the following. Our second claim says that if a and b are integers that are not both 0, then the GCD of a and b is equal to the GCD of a and b plus at for all t in z. So this says that if I take b and I add any multiple of a to it, the GCD is unchanged. Okay, so let's prove this. This also is a fairly straightforward proof. Okay, so let's set up some notation. I'll say suppose that d is the GCD of a and b, and d prime is the GCD of a and b plus at, right? And so now our goal, we can just write this down so we have it on the side. Our goal is to show that d is equal to d prime, right? We want to show that these two quantities are actually the same. Okay, so let's write down what we know. So we know that d divides a and d divides b, right? By definition of GCD, d has to be a common divisor of a and b. So by claim 1, d must divide b plus at, right? b plus at is an integer linear combination of a and b. So hence, what do we know? We know that d divides a and d divides b plus at, so d has to be less than or equal to the greatest common divisor of those two. So we have that d is less than or equal to d prime. Okay, so what's left to show? We want to now show that d prime is less than or equal to d. So how do we do that? Well, we know that d divides a, or rather d prime divides a, and d prime divides b plus at. Right, so d prime is the greatest common divisor of a and b plus at, so it has to divide both of them. And now what I'd like to do is take a clever integer linear combination of a and b plus at in order to produce b. So what am I going to do? I could say, okay, by claim 1, we have that d prime must divide a times negative t plus, we could say 1 times b plus at, or just plus b plus at. And what does this mean? Well, this is just another way of saying d prime divides b. So hence, we know that d prime has to divide a, and d prime has to divide b. So it's a common divisor of a and b, and so d prime is less than or equal to d. Okay, now we can put our pieces together, right? We have that d is less than or equal to d prime is less than or equal to d, so let's put these two together. We'll say since d is less than or equal to d prime, and d prime is less than or equal to d, we have that d is equal to d prime. And that finishes our proof. And this is going to be really important in proving that our algorithm actually works. So we'll get to the algorithm now. So we're finally ready to talk about our Euclidean algorithm. So first we'll talk about a little bit on how the algorithm works. We'll give a proof that it actually does what it's supposed to do, and then we'll do a few numerical examples. Okay, so the Euclidean algorithm is quite simple. It's just repeated uses of the division algorithm. So what we're going to do is we're going to start with two integers a and b, and we'll assume b is bigger than 0. And the division algorithm tells us that I can find integers q and r that allow me to express a as bq plus r, and r is bigger than or equal to 0 and less than b. And now what I'm going to do is I'm going to look at b and r and apply the division algorithm to these two. So if I apply the division algorithm to those two integers, I'll notice that b can be written as r times q1 plus r1 for some integers q1 and r1, and r1 is strictly less than r and bigger than or equal to 0. Okay, so what I'm going to do now is take this r and this r1 and apply the division algorithm again. And you kind of see where this is going. So I can say that there exists integers q2 and r2 such that r is equal to r1 q2 plus r2, and r2 is strictly less than r1 and bigger than or equal to 0. Then you can probably guess what I'm going to do next. I'm going to take r1 and r2 and apply the division algorithm to those. So I can find integers q3 and r3 satisfying these properties. And you can imagine I'm going to keep going. And eventually what's going to happen if I do this is I'll notice that the process stops. And the question is, why does the process stop? Well, like eventually I'm going to hit a remainder of 0 is what I mean when I say the process stops. So the process terminates because every remainder that I find is at least one smaller than the previous remainder. So we know that r is strictly less than b. Then I notice that r1 has to be strictly less than r. I notice that r2 has to be strictly less than r1. r3 has to be strictly less than r2. And what I notice is that I'm starting with a b and I'm working my way downward. Eventually I'm going to have to hit 0, right? Remainders are always bigger than or equal to 0, so it's not like I'm going to go negative. Eventually I'm going to hit 0. So we know that this process is going to stop in finitely many steps. Okay, so now we're ready to prove a claim. The claim I'm going to make is that this last remainder here is actually the GCD of a and b. So I'm going to write this down. I'm going to prove that Rn is the GCD of a and b. And what I'm going to do is essentially just make repeated uses of claim 2 from earlier. Okay, so what do we notice? The first thing we notice is if I look at this equation, this is essentially telling me that Rn divides Rn minus 1. So the first thing I'm going to notice is Rn divides Rn, and Rn divides Rn minus 1. So I can say that Rn must be the GCD of Rn minus 1 and Rn. So this is the largest divisor of both Rn and Rn minus 1. Okay, so what am I going to do? I'm now going to apply claim 2. By claim 2, I can say that this is equal to the GCD of Rn minus 1, comma Rn plus Rn minus 1 Qn. And we might notice that this expression that I've just written down here, this Rn plus Rn minus 1 Qn, this is just Rn minus 2. Okay, so this is just going to be Rn minus 1, comma Rn minus 2. So this is using our claim 2 from above. And I'm going to just continue this process now. I'm going to notice that, well, this is just going to be, well, let's rewrite this. This is the GCD of Rn minus 2, comma Rn minus 1. So let's rewrite the thing in the second slot. I know that this is going to be the same as the GCD of Rn minus 1 plus Rn minus 2 times Q sub n minus 1. And this guy right here is just going to be the GCD of R sub n minus 2, comma R sub n minus 3. Okay, and we just continue in this way, right? Eventually we'll reach this point where we have the GCD of R and R1, and this will give me, well, this is the same as the GCD of R and R1 plus R times Q1, which we might notice is the GCD of R and B, which is the same as the GCD of B and R. And then we might finally use finally notice and use claim 2 again and say that this is the GCD of B, and R plus BQ, which is the GCD of B and A, which we know is just the GCD of A and B. So this proves my claim. Okay, so in our first application of the Euclidean algorithm, we'll find the GCD of 45 and 27. Okay, so what we're going to do is just, again, repeatedly apply the division algorithm. So I'm going to say, okay, 45 is going to be 27 times 1 plus 18. Then I'm going to look at this 27 and this 18 and apply the division algorithm to those. So I'm going to get that 27 is 18 times 1 plus 9. Then I'm going to look at this 18 and 9 and apply the division algorithm to those. So I'm going to say 18 is 9 times 2 plus 0, and I've reached a remainder of 0. So what does my Euclidean algorithm tell me? My Euclidean algorithm tells me that this guy right here, this last non-zero remainder, is the GCD. So what I can conclude is that the GCD of 45 and 27 is equal to 9. Okay, so let's try another one. Let's try to find the GCD of 128 and 423. So what I'm going to do is I'm going to write 423 as 128 times 3 plus 39. So I've used the division algorithm to rewrite this, and now I'm going to look at 128 and 39 and apply the division algorithm to those. So I'll say 128 is 39 times 3 plus 11. Okay, and now I'm going to look at the 39 and 11 and apply the division algorithm to those. So I'll say 39 is 11 times 3 plus 6. And then I'm going to look at this 11 and this 6 and apply the division algorithm to those. So I'll notice that 11 is 6 times 1 plus 5. Okay, so then I look at this 6 and this 5. I apply the division algorithm to those. So I get that 6 is equal to 5 times 1 plus 1. Okay, and then I look at this 5 and this 1 and apply the division algorithm to those. So I'll get that 5 is 1 times 5 plus 0. And I finally reached my 0 remainder. So what does this tell me? It tells me that this guy right here, this 1, this is my GCD. All right, it's the last remainder that occurs before you hit a 0 remainder. So now I can conclude that the numbers 128 and 423 are relatively prime, that their greatest common divisor is 1. All right, and let's do one more example. So I want to find, let's say, the greatest common divisor of 236 and 128. I know that they're both even, so the greatest common divisor is going to be at least 2. But let's try to figure out what this is. So I'll say 236. I'll use the division algorithm. I'll write this as 128 times 1 plus 108. Okay, and now I use the division algorithm on 128 and 108. So I'm going to get 128 is 108 times 1 plus 20. And now I'm going to use the division algorithm on 108 and 20. And let's see what we get. We're going to get 108 is 20 times 5 plus 8. Okay, so I use the division algorithm on 20 and 8. Let's see what we get. We get 20 is equal to 8 times 2 plus 4. Okay, so I use the division algorithm on 8 and 4, and let's see what we get. We're going to get 8 is equal to 4 times 2 plus 0, and I've hit my 0 remainder. So that means I know what my GCD is. My GCD is going to be this number right here. It's the last non-zero remainder that occurs. So my GCD of 236 and 128 is actually going to be 4. Okay. All right, so our goal now is to develop what's called the extended Euclidean algorithm, and what I'd like to do is just use the steps in the Euclidean algorithm to rewrite the GCD of A and B as an integer linear combination of A and B. So Bézout's lemma claims these integers u and v exist, that these integers u and v such that AU plus BV is the GCD exist, but Bézout's lemma doesn't tell us how to find them. So this extended Euclidean algorithm actually tells us how to find them. So we're going to do this by example. So I'm going to start with this example from earlier about finding the GCD of 236 and 128. So these are the steps from this previous example. And what I'm going to do is I'm going to take each one of these equations and solve it for the remainder. So I'm going to take each one of these equations and rewrite it this way. So I'm going to take 108, this 108 here, and rewrite it as 236 minus 128 times 1. And it's important that I leave it in this format. I'm going to take 20 and rewrite it as 128 minus 108 times 1. I'm going to take 8 and rewrite it as 108 minus 20 times 5. And I'm not going to expand these. I'm just going to leave this in this format. Okay, so let's explain how this works, but first I'll make a little bit more space. Okay, so the very first thing I'm going to do is just take this last equation that we've written down and rewrite it. So I'm going to take this equation down here and rewrite this one. So I'm going to say 4 is equal to 20 minus 8 times 2. Okay, and the first step that we're going to take after that is we're going to single out this 8. So I'm going to slowly replace numbers. And what I'm going to replace this 8 by is this expression right here. So let's do that. I'm going to say that this guy is 20 minus, and now 8 is getting replaced by 108 minus 20 times 5. So let's write that in parentheses. I'll say 108 minus 20 times 5. And I'm going to leave that 2 on the outside. So I'll say times 2. Okay. And I'd like to simplify this, but in simplifying it, I want to make sure I'm preserving my 20 and my 108. So I don't want to expand this out or do something like that. I want to make sure I'm preserving my 20 and my 108. Essentially, I just want to preserve all these numbers that are going to appear as remainders, and 236 as well, and 128 as well. So I want to just make sure I'm preserving these numbers as I'm rewriting things. Okay, so let's take a look at what we have. Well, the first thing that I might notice when I'm looking at this expression is how many 108s do I have? Well, I notice that there's a negative times 108 times 2. So I'm going to simplify this out as 108 times negative 2. And then I'll also notice that there's a 20 here, and there's a negative 1 times 20 times 5 times 2. Okay, so what's that going to leave me with? This is going to leave me with a negative and a negative become a positive, but I have 20 times 5 times 2, so there's going to be 10 copies of 20 over here and 1 additional copy of 20 over here. So that's going to give us a total of 11 20s. So I'll write this as 20 times 11. Okay, great. So now I've rewritten 4 using 108 and 20. What's my next step? My next step is going to be, can I replace this 20? Well, I have an equation for doing that, so let's replace the 20. And the thing to remember here is that I'd like to preserve the 128s and the 108s when I do this. So let's rewrite this. So this is going to be 108 times negative 2, this one stays, plus the 20 is going to get replaced by the following. It's going to get replaced by 128 minus 108 times 1. And then we still have this times 11 hanging out on the outside over here. Okay, so let's see what we have now. When I rewrite this, let's first look at how many 128s I have. I notice that I have 128 times 11. So I have 11 copies of 128, so I'll write 128 times 11. And then I want to ask myself, how many copies of 108 do I have? Well, let's take a look. I have negative 2 copies of 108 here, and then I'm going to have negative times 108 times 1 times 11. So I'm going to have negative 11 copies of 108 over here. So I have negative 2 copies here, negative 11 copies here, so that's going to give me 108 times negative 13. There's a total of negative 13 copies of 108. Okay, so now we've written 4 in terms of 128 and 108, and the last thing we'd like to do is to rewrite this 108. So I'm going to take this 108 that we have here and just replace it with this top equation. All right, so let's do that. So 128 times 11 stays as is, and the 108 is going to get replaced by 236 minus 128 times 1. And then I'm going to have this negative, whoop, forgot to change the color. I'm going to have this negative 13 over here. Okay, and then I finally ask myself, well, how many copies of each number do I have? I'm going to have 236 times negative 13, so I have negative 13 copies of 236, so this is going to be 236 times negative 13, plus, how many copies do I have of 128? Well, there's 11 copies here, and there's going to be negative 1 times negative 13 copies here, so there's going to be 13 copies of 128 here, 11 copies of 128 here, so this is going to give me 128 times 24, because 13 plus 11 is 24. right? So what have I done? I now have that 4 can be expressed as 236 times negative 13 plus 128 times 24. So there's my integer linear combination. Finally, I'd like to end with an exercise if you'd like to try a problem yourself. The exercise is to basically repeat this process, but find integers u and v such that 1 is equal to 128u plus 423v. Right? So it's the same process just for one of our other examples.